Hi everyone, this is Electric Fields Lesson 7, Electric Potential and Potential Difference, part of the A-Level Physics. It's on every major exam board. Electrical potential, V. So, just go for the definition first, and then we'll link it to gravitation. So the electric potential of a point within an electric field is equal to the work that must be done per coulomb of positive charge, that's important, in bringing the charge from infinity to the point. So that's the same as gravitational potential, really. It's just electric instead of gravity. So gravitational potential is the amount of work done in bringing a unit kilogram mass from infinity to a point within a field. Same thing, just electric instead of gravity. So some notes. So electric potential at infinity is 0. The exact same with gravity. Gravitational potential at infinity is also 0. Points around positive charges have positive potentials, and points around negative charges have negative potentials. Electric potential is measured in joules per coulomb, or more commonly volts, where 1 volt is equal to 1 joule per coulomb. And finally, really important, electric potential is a scalar quantity, which is the same as gravitational potential. Gravitational potential is also a scalar quantity. You need to be mindful that, so if we just do a quick comparison, the electric force is a vector, electric field strength is a vector, electric potential is a scalar. It's the same with gravity. Gravitational force is a vector, gravitational field strength is a vector, gravitational potential is a scalar. So be mindful of that. So let's have a look. What's the equation? Well, the equation for electric potential is V equals, so it's the charge divided by 4 pi epsilon naught r. These are obviously for radial field, so point charges. So remember, epsilon naught is on data sheets is 8.85 times 10 to the minus 12 farads per meter. It's the permittivity of free space. So if you want to pause and get that written down, remember it is a scalar quantity. Really important. And then I'm going to give you a shorthand version of this, which I use. So if you're just going to remove this, you can also use V equals KQ over R. And K is just 1 divided by 4 pi epsilon naught. And I remember this for simplicity and for quickness. So K would be 8.99 times 10 to the power 9. You don't have to use that version, I just use it because it's quick. However, in some instances, as you'll see later, you have to use the other version regardless. Okay, let's move on. So another quick one, electric potential difference. When a charge Q is moved for an electric potential difference, delta V, the work done is given by work is charge times change in potential. Which is, it's basically the energy is charge times voltage, or potential difference, from, year 10, from GCSE. The gravitational potential difference is, I'm just going to write this here, the gravitational one is the work done is mass times change in potential. So basically the same thing, just swapping the masses for a charge. So work done is charge times voltage, essentially. So if you want to get that down as well, if you want to pause and get that, and then let's move on. So quick questions. So if you want to pause and do this one, calculate the work required to move a charge of 40 millicoulombs between 2 electrodes of potential difference 5 kilovolts. So the work done, the energy, is the charge times change in potential. So the charge is 40 millicoulombs, so 40 times 10 to the minus 3, multiplied by the potential difference, which is 5 kilovolts, 5 times 10 to the 3. Put that in your calculator, that will give you 200 joules. That should be fine. Let's have a look at the next one. Calculate the work required to move an electron of charge 1.6 times 10 to the minus 19 coulombs between two electrodes of potential difference 1 volt. If you want to have a go at this, please do. So, work done with energy gained is charge times change in potential, so QV. So the charge is the charge of the electron, so 1.6 times 10 to the minus 19 coulombs, multiplied by 1 volt. And that gives us a gain in energy of 1.6 times 10 to the minus 19 joules. You might think that's a strange question, but it's actually the definition of the electron volt, because that would equal 1 eV. Just a bit of revision. Right, let's move on. So electric equipotentials, the exact same as gravitational equipotentials, but just electric instead of gravitation. So there are surfaces that join at points of equal potential, and no work is done by the electric force when a charge is moved along an equipotential surface. And equipotentials are always perpendicular to the field, the exact same as when we deal with mass and gravitational fields. So for example, if you were on, say, this point, so we could calculate that potential, V equals KQ over R, whatever it may be. But if we move around, say, from there to here, our change in potential, our potential at these 2 points, so if we did V equals KQ over R at this point, the values would be identical. So if we tried to do work done, it's charge times change in potential, our change in potential is 0. So work done is also 0. So no work is done by the electric force when you moved along an equipotential surface. So work done against, what you would say is work done against the field is 0. Commonly comes up as multiple choice questions, quick fire knowledge. Okay, let's move on from that. So here's a question. If you want to have a go, just pause. Please complete this and then I'll take you through it when you're ready. So part A, calculate the electric potential at A, which is 3 meters away from a point charge of 1 microcoulomb. So we need to do electric potential is KQ over R. Just going to put some numbers in. So K is 8.99 times 10 to the power 9. Multiplied by the charge, which is the 1 microcoulomb charge, so 1 times 10 to the minus 6, divided by the distance that separates them, 3 meters. And that gives us, if you calculate that, 2,996 point recurring 6 joules per coulomb, or volts. What I'm going to do is just say 3 kilovolts, or 3,000 volts. Don't worry if you've not rounded up. If you've got 2,997, that's perfectly fine. So the next one says, part B, calculate the electric potential at B 6 meters away. So I don't need to do the calculation, I can just look at the relationship. So V is equal to KQ over R, which means V potential is proportional to 1 over R. So essentially what we've done is double the distance. So if we've doubled the distance, we would halve the potential, as they're inversely proportional. So that'd be approximately 1500 volts for part B. So part C, I'm just going to clear this. Remember, if you need to rewind at any point or pause, please do. So part C, how much work will be done in moving a 2 microcoulomb charge between points A and B. So the work done is charge times the change in potential. So the charge is the 2 microcoulombs, so 2 times 10 to the minus 6. Change in potential, well, we had 3,000 volts and 1,500 volts. So the difference between them would be 1,500 volts. So if we multiply them together, we get 3 times 10 to the minus 3 joules. Or you might have written 3 millijoules. Which way would you be moving, so part D, which way would you be moving this small charge if you were doing work against the field? Well, it's a positive charge, So to do work against the field, we'd have to move it towards the other positive charge. So if you said towards the 1 microcoulomb charge or to the left, they're both correct. Okay, let's move on from there. So you can get questions like this. So what I'm going to do is use this as an example, and then I've got another similar question that you can have a go at after. I'm going to give you a quick way of doing these. So two charges P and Q are 100 millimeters apart. So you've got a 4 microcoulomb charge at point P and a minus 6 microcoulomb charge at point Q with a 100 millimeter distance between them. And it says X is a point on the line between P and Q. If the potential at X is 0, what is the distance from P to X? So we've got some random point there, X, and this question wants to find this distance. These again can come up as multiple choice. So what you should do is the distance, so you just do, this is pretty easy actually, I know it sounds difficult, but it's execution of this is pretty straightforward. 100 millimeters, and then you do the difference in charge. So the difference in charge is minus 6 to 4. So that difference is 10 microcoulombs. So what we'll do is this. So you do 100 millimeters divided by 10 microcoulombs. So what you get is 10 millimeters per microcoulomb. If you look at the units, millimeters per microcoulomb. So that means to go, to shift a microcoulomb, you need to go 10 millimeters to the right. So we need to go from plus 4 to 0 essentially. Microcoulomb. So that'd be 4, 3, 2, 1, 0. So we actually need to move across 4 microcoulombs. So if I multiply by 4 microcoulombs, you'll see the microcoulombs cancel, and I'm left with 10 millimeters times 4, which is 40 millimeters. So we need to move 40 millimeters to the right. So that's the technique. Hopefully that's okay. I'm going to give you another example on the next page. I want you to have a go at it yourself, see if you can get the right answer. Okay, if you want to pause and have a go. So once again, the diagram shows two charges, plus 4 and minus 16 microcoulombs. This time they're 120 millimeters apart. What is the distance from the 4 microcoulomb charge to the point between the two charges where the resultant electric potential is 0? So what we need to do is the distance, 120 millimeters, divided by the change. So we've got minus 16 and 4, so that's 20 microcoulomb difference. That gives us a gradient, so to speak, of 20s into 120 of 6 millimeters per microcoulomb. And we need to move from plus 4 to 0. So we need to move 4 microcoulombs. So we're going to multiply by 4 microcoulombs. The microcoulombs are going to cancel yet again. And we're left with 6 millimeters times 4. So 6 times 4 is 24 millimeters. Hopefully that went okay. Right, we've got another example, pretty tricky one. Let's have a look at it. So this diagram shows 2-point charges of magnitude plus Q and minus 2Q, placed a distance r apart. And what I would like to do is to attempt to show that the potential at point P, this point, is minus 3Q over 8 pi epsilon naught r. And this is the example that I spoke about earlier, where you can't use K, we have to use the full constant for 1 over 4 pi epsilon naught. So if you want to pause and have a go at this, try and show that, and then I'll take you through the answer. So let's look at, from each point, we need to just apply the equation. So the equation is, potential is, instead of KQ over R, I'm going to use Q divided by 4 pi epsilon naught R. So from the plus Q charge, we've got a distance of 2R. So we can use this equation, and we're going to put a 2 in front of the R. So, but obviously 4 times 2 is 8. So the potential from at point P from the first charge, the Q, would be, the potential is Q divided by, now we've got 2 times R, so we'd have 4 times 2, so that's 8 pi epsilon naught R. Okay, then we can get the other potential from the minus 2 charge, so that potential would be So it'd be minus 2q, because that's its charge, 2 lots of q, divided by, now the distance is r, so it would just stay as 4 pi epsilon naught r. Now, because potential is a scalar quantity, we just need to add these together. So obviously we're going to multiply this one on the right by 2 to get the denominators the same. So if we times that one by 2, we would end up with minus 4q divided by 8 pi epsilon naught r. So our total sum, so the first one would stay the same, 8 pi epsilon naught r, minus, because it's negative, then this times 2, so minus 4q divided by 8 pi epsilon naught r. So now the denominators are the same, it's simply q minus 4q. So q minus 4q is minus 3q, and then the denominator obviously stays the same, so that's 8 pi epsilon naught r. So what we've done is show this. So that's our answer. Hopefully you figured that out. If not, you might want to rewind and attempt that again. Just make sure that you can do that style of question. And then we've got one more left. So good question this. Pretty straightforward, but what I'm going to do is explain the answer, which can be, many times more difficult. So if you want to pause and have a go. So which of the following statements about electric field strength and electric potential is incorrect? So you've got A, B, C, or D. So we can get the answer simply by eliminating what's obviously wrong. So electric potential is a scalar quantity. That is obviously true. Electric field strength is a vector quantity. That is also true. The potential gradient is proportional to the electric field strength. Well, if you remember from lesson 1, in uniform fields, electric field strength is equal to change in potential over change in distance. So the potential gradient, delta V over delta D, is proportional to E, the electric field strength. So that is also correct. So what's incorrect is C. Electric potential is 0 whenever the electric field strength is 0. So that is what is incorrect. So C is the answer via a process of elimination. However, if you want to think about this and then maybe pause, could you show that this is incorrect? Can you show that you can have an electric potential without any electric field strength? If you want to pause and have a go at that. If not, I'll give you an explanation. So imagine two positive charges, and we look equidistant in the middle. And these charges they're the same charge, so let's call them Q. Now in the middle, let's say that the distance is the same. The potential, so KQ over R for each point, would be identical. So we could have maybe, 3 kilovolts from each side. And remember, because potential is a scalar quantity, these would just add together. So we would have an electric potential of, say, 6 kilovolts in total. Whereas electric field strength is a vector quantity. So the electric field strengths would be, numerically equivalent. They would be the same. However, they're in opposing directions, so they would actually cancel out. So in this scenario, you'd have an electric field strength of 0 newtons per coulomb, but we would still have this 6 kilovolt electric potential. So that's a way of explaining it. Anyway, I hope that's been useful. Take care and I'll speak to you soon. Thank you.